This I probably, yeah, I just put this for a guide to myself. So that's not important. But so the first topic is polar area. So we can remember from geometry that the area of a sector of a circle uh, as a function of theta is 1/2 r squared theta. So when theta is 2 pi, then we uh, we have normal area of a full circle, which is, pi r squared, because you would have 2 pi times 1/2 times r squared. So that's a fact we'll need later. So actually right here, so area and polar coordinates. So it's just exactly this. We use this formula to approximate uh, area and polar coordinates. So we use sectors of a circle to approximate, or you really get the exact area of these regions and polar coordinates. As opposed to in single variable calculus, thus far we have been using rectangles uh, for our approximating shape in integration, but now we're using area as the sector of a circle to approximate this area. So, and then I drew a little picture and a little explanation. So subdivide the interval theta going from alpha to beta into n+1 subintervals of equal width, delta theta, which we define as theta I plus 1 minus theta I. We choose an element in that interval, the ith subinterval, and we use that in our f of theta function right here, our f of theta function. So this approximates the ith slice. So like this little pizza slice right here of the region bounded by this polar function. And so simply we take the sum of all of these delta AIs, this small areas. Really, it shouldn't be a delta AI. It should just be AI. So ignore the delta right here. But so the area of the ith sub, area sector, ith subsector is so the sum of all those would be the total area, and then we do the trick where we take the limit of the Riemann sum, and that turns into integration. And then this is like the formula you use, which was on the previous slide. So just write down this formula, and this is the formula you use to find area and polar coordinates. One other thing that you might need to know for polar area would be it would be the area between two regions, like inside of one and outside the other. So in that case, you would do big R squared minus little r squared in the integrand. We didn't write that on. I didn't write that on here anywhere. But I know it was in some of the homeworks, some of like WebAssign or whatever. So yeah, that might also come up. Area enclosed between two polar regions. We have polar arc length. So like if this was the integral calculus of polar, this is the differential calculus of polar, right? I mean, we need derivatives to calculate it, though. I mean, we're still integrating, but no, yeah, this is still integral calculus. I'm sorry. I was thinking of like tangent lines. So yeah, so I just kind of derived this arc length formula right here. So r is a function of theta. we know this from polar coordinate transformation. X equals r cosine theta, y equals r sine theta, but r is a function of theta, so we can replace r with f of theta in both of these. Then take the derivative with respect to theta. We need a product rule to do that on both x and y. So take the derivative of the first, keep the second. Well, it's minus because the derivative of cosine is negative sine, but plus, the first times the derivative of the second. So we do that on both of these, and then we calculate. So like you can kind of think of what x and y do. You can think of these as a parameterization of the curve from an interval to a curve in R2. So that's kind of important because from earlier on in this calculus sequence, we got a formula for arc length of parametric arc length. I think it's in chapter 10 of Stewart's calculus, the textbook for this class. I think that's the textbook. I'm not sure, but so yeah, it's just basically just this magnitude of r prime of theta down here, and then this is just all the calculations for r prime of theta. Where this was bad notation on my part, but this vector r right here, this vector r is really the parametric equation for the curve drawn out by this little r. So but yeah, so basically, it's just the magnitude of the derivatives, the sum of the squares of the derivatives. Yeah, the magnitude of the velocity vector. That's all arc length is. It's just the magnitude of velocity vector. And when we have this parameterization, well, I just calculated the magnitude of velocity vector right here, and so I can just plug it in directly, right? We have the square root because that's magnitude. And yeah, so this is the arc length formula, which is like once again magnitude of velocity vector. So now we have space curves. So C is a set of all x, y, z in R3 where these three functions, when you plug in the t value, you get that x, y, z out. So since there's only one parameter, it's a space curve. If you had more parameters, then it would be a higher dimensional object. But there's one parameter t, and we're just considering the set of all these points that these functions map to from the interval. And then the space curve is the position in three-dimensional Euclidean space. So we can kind of have a picture right here. R maps from an interval t to a space curve. And these parameterizations are not unique. We can have different speeds, different velocities, stuff like that. So I gave an example. So we have some parameter. We have r, some function r mapping 0 to 2 pi into R3 space. And we define it to be a circle of radius 1 centered at 0, 0, 1. So we have r of t equals cosine t sine t. Cosine t sine t, we know that just parameterize a circle in the xy plane, and we we add the z as 1 component to make it on the z equals 1 plane. Yeah, so then we calculate r prime. R prime, you just take the derivative of the components. Take magnitude of r prime, you'll find it's 1. So this is a special curve. We have a parameterization for this curve that has arc length or speed really, speed 1, which is also called arc length parameterization. So that's nice to have in calculations, so like calculating. We'll get to later on the tangent, the normal, and I don't think you talk about binormal, but also it would be easier for curvature. But on the other hand, we have r sub 1, and this maps from a smaller interval into R3, and it's the same exact shape, but it has speed equal to 5 constant. So yeah, just an example. So, or alternatively, we could have made r sub 1 go from 0 to 2 pi, the whole interval that r is on, in which case it would travel around 5 times in the same amount of time r travels around once. So it's just going a lot faster. So definition of velocity and acceleration. X and y are twice differentiable functions of t. R is a vector value function given by r equals x of ti plus y of tj. Then the velocity vector. It's just exactly what you would think. You know, you take the derivative of each component once, twice. We require it to be twice differentiable because acceleration requires 2 derivatives. But since, you know, this r is a position function, we know from physics or from earlier on in this calculus sequence, you know, the derivative of position is velocity, and the derivative of velocity is acceleration. Does anyone know what the name for the derivative of acceleration is? Yeah, it's jerk. Jerk. And then, yes, we have speed. Speed is magnitude of velocity. It's always positive, right? We know magnitude is sort of like a distance. So when you see the double bars, whenever you see those double bars, that just means it's always greater than or equal to 0. And it equals 0 when? Does anyone know when speed equals 0? What's the only time speed can be 0? Yeah, v is 0. It would have been nice to use boldface in that, because it's like, yeah, it's like saying well, it's just a property of the magnitude, really. So the property of the magnitude is it's greater than or equal to 0, and it equals 0 if and only if the vector we're taking the magnitude of is 0 vector itself. So like the only vector that has distance 0 from the origin is the 0 vector. It's kind of like saying the 0 vector is unique in a way. There's only one vector that has distance 0 from the origin, and that's the 0 vector. And then this is just to remind you a little bit about tangent lines, and then also what a derivative is. So tangent line at a point on the space curve is the line centered touching at P. and then it has to be parallel to the velocity vector. And then I use this limit of a difference quotient to define velocity vector. And then there was a picture I wanted to add that we can imagine over here. So this is a position function, right? This is the position of a like object flying through space or something, and you can realize r of t as a vector pointing from the origin to a point. Can you guys see my mouse when I move it? I don't know if you guys can. Did you see my mouse like pointing at the, okay, you did. Okay, thank you. So yeah, we're you can imagine r of t being a vector pointed from the origin to the point on the space curve. And then all we're doing is taking a slight step along the curve and then taking the difference of those two vectors. So like we have a vector pointing here, and then we have a vector at like t plus h, and t plus h is just a small step past t. And we take the difference of those two vectors, and then that's just the velocity vector. So yeah, maybe try on your own to draw a picture as to why this expression is the velocity vector, to see for yourself. This is nice. We know this from kinematics. What this is saying is if we have a projectile, it follows a parabola. So you have x being linear in t, and you have y being quadratic in t. So since x is linear in t, y is quadratic in t, it's a parabola, and it opens either up or down. And it actually specifically opens down because g is negative. And we can only do this because gravity is constant, or the acceleration of this object is constant. So the acceleration is constant at g for y, but the x acceleration is 0. There's no x acceleration. So really, these formulas can be found. Just integrating acceleration. So like we have y equals negative g, or we have y equals negative g. That's the acceleration, and y is negative g. And then we integrate that twice with the proper initial conditions. That being the speed in the y direction and the height in the y direction. And that's where the v naught sine theta comes from. This is the initial speed in the y direction. And then this h is just the initial height. So this is like a very simple differential equation for like acceleration. So like the second derivative of position equals negative g. And then this is an even simpler differential equation. This is a sub x, or you could call that like x double prime of t equals 0, because there's no acceleration in the x. So that's why we can use these formulas for this projectile motion, because we have this constant acceleration. Otherwise, it would be a lot harder problem to solve. And if you take Math 2420, then you'll probably run across some problems like that, where you won't neglect air resistance and stuff. Tangent vectors. So yeah, this is where it gets messy to calculate. So remember earlier we had that curve. We had this curve with arc length parameterization right here. So this top R right here, this guy, he was speed 1. He had arc length parameterization. So that means that when we calculate t for him, t is just equal to r prime, because t equals r prime divided by magnitude of r prime. We don't have to keep track of dividing by this magnitude of the derivative whenever we don't have to keep track of this guy whenever the magnitude of r prime is 1 for all t, which is a very nice property to have. And you can obtain that property. You can take curves under certain conditions. You can take curves that don't have unit speed parameterization or arc length parameterization, and you can make them that way through this arc length parameterization. And then as a result, the t vector will just be r prime, and you don't have to remember all these formulas that come up after this. I think the n is the same in either case, but still, it would just be a lot easier to calculate than whenever you don't have arc length parameterization. So definition of principal unit normal. It's defined in this way: t prime divided by magnitude of t prime. So it's it's a unit vector. And then we can decompose the acceleration into tangential and normal components, and we have some formulae for that. Arc length. So yeah, like I said earlier, arc length is the magnitude of the velocity. You can just remember this one. Don't remember the square root. You already have magnitude memorized. Well, so then you can just not have to write this on your formula sheet or whatever. You can just write magnitude r prime. And yeah, so that's just something we know from even single variable calculus, when our parameterization was only had 2 components in it, and it was magnitude of x prime of t squared plus y prime of t squared, and then there was no z. And we actually used that for the polar earlier to deduce the arc length of a polar curve. Yeah, so this is arc length parameterization. The speed is 1. Those are nice to have. So whenever speed is not 1, there's this formula for curvature. Curvature, you can think of curvature as like 2-dimensional turning. Question, is it a scalar or a vector? Is curvature? Yeah, it's a scalar. So yeah, we have magnitude of so r prime is like velocity. Yeah, it's just a number. So r prime is velocity and r double prime is acceleration. The cross product of those produces a vector that is orthogonal to both of them. And then we take the magnitude of that, which would give us a number. And then magnitude of r prime of t to the third, that is just this speed raised to the third. I can go back to that. This one. You're welcome. You good now? Okay. Let's see. Cool. And then if it's a plane curve, well, not even a plane curve. This has to be a function of one variable. So if we have like the graph of a function of one variable, then we have this other formula for curvature. Though I'm sure that this one would still work. You would just have a different. You would have a silly parameterization. You would have x comma f of x comma 0, and you could use this same formula. And we have a summary. So curves in the plane, they don't have a z component. Curves in space, they do have a z component. Velocity is the first derivative. Speed is the magnitude of velocity. Acceleration is the second derivative of position. And then this is a I think this is something called a Frenet frame. This is one of the Frenet formulas for the binormal. It's a derivative. It doesn't matter, but so yeah, basically we can like decompose like these this t and n vectors. They're very special. And there's another vector called b that they don't include here, but you can get b by taking the cross product of t and n. And so you can like represent a lot of things with this t, n, and b. This t, n, and b is like an orthonormal basis on the curve, and it's like specific to the curve. So we can represent things in like the derivatives, or this t, n, and b of the curve. So like t is this, n is this, right? Just remember these formulas. And then we have this tangential acceleration, normal component of acceleration. We have several different forms of it. So whichever form you prefer, there might be one that's easier to use. I think the first one, I mean, if you already have n, but it might just depend on what you have. And then formulas for curvature. So you just want to take a picture of this or something, and then remember all these formulas. Yeah, partial derivative. So it's the same, right? The limit of the difference quotient, it's the same as a regular derivative, except we have another variable that we're not touching. So we don't touch the y. We're only taking a small change in x. So you fix y and change x just a little bit, and you fix x, and then you change y a little bit for the other partial. We denote it f sub x, f sub y. If these limits exist. If they don't exist, then it's not differentiable. The mixed partials are equal if they are continuous. So you can construct an example of a function that has mixed partials not equal. But the only catch would be the fx and f well, so fxy and fyx are not continuous. So we like smooth derivatives, derivatives that are continuous and we can take derivatives of. And so I do a little example. Does anyone know what surface this is? F of x equals x squared plus y squared. Yeah, paraboloid. And then this is kind of me proving to you, you can do regular calculus with this weird definition of a partial derivative. So, right, we fix y as a constant. So when we add a constant, we take the derivative of a constant, that goes to 0. So that's why that kind of melts down. You can see it go down exactly right here. Right, we didn't change it at all, so it's just like adding a constant, and they cancel, and we expand the rest of the square, and we cancel the t's, and we get 2x, which is exactly what you'd expect. Differentials, it's like a linear approximation. So the total differential is, so this, like, I guess this delta, right, this delta z is the exact change in z. This exact change in z, right, because like what this is saying is like we're basically like on a surface, a function of 2 variables, or maybe we're on like a function of 3 variables or more, and we know the value of like z0 right here. Say we know that, but we want to find z1. Okay, well, we need to approximate this delta z, the small change in z. We want to see how much z is changing as we take a small step away from our point x naught, y naught. So, and then we have this formula, which turns out to be, this gradient dot product with the differentials, how much we're changing x, how much we're changing y. And so if you really think about it, all this is like using a tangent plane to approximate a function of 2 variables to 1 variable. Yeah, I mean, it's basically just, the tangent plane. So like you can make an analogy to single variable calculus where we would approximate with the linearization. Yeah, the linearization was first order Taylor polynomial, and it was a line, and we use that to approximate, like the square root of a weird number or something like that. So we can do the same thing with, functions of several variables. We have the chain rule. I really don't like how any book can like word it, because I think the best way to see it is like in action. Yeah, so I think this diagram works better than like any sort of like words you could read about it, because like you just draw like how the independent variables are related to the function, right? We have our f is a function of x, y, z, and t. Okay, so we're saying that x is a function of u and v, y is a function of u and v, z is a function of u and v, and then t is a function of s. So these x, y, z, these are spatial variables, and t is like a time variable. Since x, y, and z are parameterized by 2 variables, that means it's like we can imagine f as like a surface changing over time. So like we have like down here, we have this UV region in R2. Well, this UV region in R2 maps to this surface in R3, and then f is also a function of t, so it could like change with time. But anyways, so if we want the derivative of this, we have to use this chain rule for several variables. So partial f respect to s, you always kind of, well, you don't always, but most of the time you look at the derivatives at the end of the chain. So we want partial f with the one down here, partial s. So we go partial f, partial t. We only have to go in one direction on this one because s is only in t. So partial f, partial t. We put the partial symbol when we have to make a choice between the branches. And then we put the d whenever it's a single variable derivative, like from t to s is just a single variable derivative, so I put a d, t, ds. And then for f, partial u, for instance, we would take the partial f respect to x and then multiply by partial x respect to u, and then just add up the rest of those, going down each branch. And then you can see it's, this is partial f, partial x, partial f, partial y, partial f, partial z. That's just the gradient, and then it's dotted with xu, yu, zu, where like that is a derivative associated from the mapping from uv to this surface. Implicit differentiation. Yeah, this is just a formula you can memorize, because like really we saw how this worked in single variable calculus. When we did implicit differentiation, I think it was like chapter 3 of Stewart's calculus book. So yeah, you can use this formula, the negative partial of f with respect to x divided by partial f respect to y. I would have to think about that for a second to say any more. We're running out of time. So then directional derivative, right? This is kind of like here we have a special directional derivative. This partial derivative is a directional derivative in the direction of the vector 1, 0. And then the partial f, partial y is a derivative in the direction of 0, 1. So whenever we do this directional derivative, we have this formula right here. This is how we define it. We're changing, it should read v1, v2 right here. So little typo. But we change, v has to be a unit vector first of all, right? Because if we make it not a unit vector, then we might change the, we would change the, like how far we're going on the, how far, like I guess how far we project. It would kind of like stretch the derivative. So we always use a unit vector when calculating directional derivatives. Yeah, so it's a limit of a difference quotient again, and we call it dv of f. So it's how f is changing in the direction of v. Because like in single variable calculus, we only had like 2 directions to go, left or right. Now we have infinitely many directions. We have like a whole circle of directions. We have like 360 degrees of directions we can take a derivative in. So there's a lot more derivatives we can look at. There's all these directional derivatives. And then, yeah, we have gradient. It's just this vector of partial derivatives, del f, the gradient of f. Yeah, it's a vector in the plane, not a vector in space. And then we'll see later on. We'll see more about this right now. So alternative form of the directional derivative. This is a theorem, so this is something you would have to prove, or that was probably proven in lecture, that the directional derivative, instead of using this nasty formula I wrote, you can just take the dot product of the gradient with the unit vector. You want to take the derivative, in that direction. So this is the practical way to do it. This is the practical way to do it. You would just take u and dot product with the gradient. Properties of the gradient. The FB differentiable at a point, gradient of f equals 0, then du of f equals 0 for all u, because that's a consequence of the dot product definition. If this guy is 0, then u dot with 0 will always be 0. And then it's the direction of maximum increase of f. Oh wait, no, the direction, the direction of maximum increase is given by gradient of f, and then the maximum increase is the magnitude of that, and then there's also a minimum. You just take the negative. And I can kind of explain why that's true with this dot product definition. You would write, equals magnitude, and then you just write the definition of a dot product, right? That's magnitude of del f times magnitude of u times cosine of theta. And so that magnitude f, magnitude u, cosine theta is maximized whenever u is in the same direction as the gradient of f. So that means the directional derivative is maximized when u and del f are parallel, and minimized when they're 180 degrees, when they're anti-parallel. And then this is the same exact thing for derivative, the gradient of a function of 3 variable. So this is just the same as this. Tangent planes, I mean, we kind of already, talked about this with the differential. But yeah, you'll use this gradient to find the normal vector to the tangent plane. And the line through the normal vector to the tangent plane is called the normal line. Angle of inclination of a plane. I don't know about this one, to be honest. I don't know what k is. I think n is the normal vector. I guess k would be, I don't know, vector on the plane. Extrema of functions of 2 variables. So this is max and mins. So let f be continuous, defined on a closed bounded region in the xy plane. Then we're guaranteed to have a minimum value, and we're guaranteed to have a maximum value. This is a very this is taken for granted. Yeah, this is, I mean, in this class, you can prove this with some other tools. I don't think that we can prove that with calculus, but I've seen it in other contexts. So like, so long as f is continuous, and then the region has to be closed and bounded, then we have a max or a min. So this would not work if f was continuous on a not closed, not bounded region. For instance, if f was continuous on the xy plane, then it doesn't necessarily obtain its minimum value or its maximum value. You can think of an easy example, just any unbounded function on, you can think of like a plane or something. You can think of a paraboloid. Anyways, so relative extrema, this is just defining it. This is what it means. It means relative minimum means all the values near f of x naught, y naught are bigger than that for all x, y near. And then for all x, y near, x naught, y naught, if the values near are less than some value, then this one is a maximum. So it's just, the same thing as single variable calculus. Extrema function of two variables. So critical point, we remember critical point from single variable calculus. It's the exact same here, just with partial derivatives. So if xy is in the domain of a function f, then it's a critical point if the partial derivatives are 0 at the same time. They're both 0, and fx or fy do not exist. So yeah, but notice that xy has to be in the domain. So like if you have like fx, fy do not exist, but xy is not in the domain, then it's not a critical point. So, but most of the time it's just using this first one. Relative extrema only occur at critical points, but not all critical points are relative extremum. The second partials test for functions of several, or I guess this is two variables. For functions of two variables, we have this discriminant. I call it discriminant D. It's fxx, fyy minus fxy squared. And we have this list of conditions that we have to know. If D is 0 in this class, you've done something wrong. I don't think they'll give you a D is 0. So either D is positive or D is negative. If D is negative, it's a saddle point. That means it looks like a maximum from one direction and a minimum from the other direction. And then we have a minimum if D is greater than 0 and the second partial of x is greater than 0. And we have this condition for relative maximum. So you guys can just remember these. Test critical points. Test 4 boundary points formed by the closed region. Determine final absolute extrema. Yeah, so test for critical points in the domain, like in the interior of the domain. And then I don't know why it has to be 4 boundary points. It could be, the region could be a circle, and then we would have like a circle of boundary points. I guess this is assuming that the closed region is a rectangle, which is not necessarily the case. But yeah, so what this is saying is like you test the interior of the region, and then you also have to test the boundary of the region. And so to test the boundary of the region, we have Lagrange multipliers. So Lagrange multipliers, they just find extremum on a constraint. So subject to g of xy equals c. And what is g of xy equals c? Well, g of xy equals c is a curve in R2. Okay. And then so we have gradient f equals lambda gradient g. This will give us this will give us 2 equations, and then we'll have a third equation from g of xy equals c, and then we'll be able to solve for x, y, and lambda. So here's the method. Yeah, we simultaneously solve, it's the number of variables plus 1, so 2 plus 1 in this case, 3 equations. Yeah. And I think that's it. Does anyone have any questions? We're gonna take a 5-minute break, and after which we will do breakout rooms, and work some problems. Consider the cardioid 1 minus cosine from 0 to 2 pi. Find the area enclosed by C. So R of theta 1 minus cosine theta. So at theta is 0, we have R is 0. Pi over 2, we have 1. Pi, we have 2. So I think it looks like pi over 4, so 1 minus 1 over root 2, 0, 0, pi over 2, 1. So I know cosine would look like this, and then 1 minus, I don't think it matters too much what it looks like, but so we know that area is 1/2 alpha to beta r squared d theta. So then this is 1/2 I think it's 0 to 2 pi though, because it's enclosed by this whole thing. I'm just afraid in choosing this. I'm afraid to go over too many times, but I think this is okay. And then 1 minus cosine theta d theta. So we can just integrate directly. Theta. Oh yeah, how do you integrate cosine of negative theta? Well, I have a trick for you. Snapchat, negative Snapchat. So you go this way for differentiation, and then this way for integration. So we are integrating negative cosine, so that turns into negative sine. So this would just be 1/2 pi minus sine of pi, 2 pi, minus 0 minus sine 0. So this is 0, this is 0, so this is just pi. Oh, they're getting 3 pi over 2. Oh, I forgot to square it. I'm so silly. Okay, so yeah, here. No one caught me. This should be squared. So then this changes the antiderivative. So this is 1/2 the integral from 0 to 2 pi, 1 minus 2 cosine theta plus cosine squared theta d theta. So this is theta minus 2 sine theta. And then how do we integrate cosine squared? We integrate cosine squared using the double angle. So this is 1/2 1 plus cosine 2 theta d theta. And then integrating this, we get 1/2 theta plus 1/4 sine 2 theta plus 1/2 theta plus 1/4 sine 2 theta from 0 to 2 pi. So then plugging it in, we get 1/2 2 pi plus pi. Everything else turns to 0 because sine of 0 is 0, and sine of 2 pi or any integer multiple of pi is 0. So this is 3 pi over 2. Okay, the next one, find the arc length enclosed by C. So if we want to find arc length, we can do that using D, L. So L is A to B magnitude R prime of T dt. So we have our curve parameterized by x equals r cosine, y equals r sine. So dx d theta is dr d theta cosine minus r sine theta. dy d theta is dr d theta sine theta plus r cosine theta. And then the magnitude of the square of these, or the magnitude of these as a vector or whatever, would be dr d theta squared plus r squared. And so we're just going to take the square root of this and integrate. So we need to calculate this. So dr d theta is sine. So this is equal to 0 2 pi square root sine squared theta plus cosine squared theta. Minus 2 cosine theta plus 1 d theta. So this is from squaring r. So, but we have sine squared plus cosine squared. So this is equal to 0 2 pi square root 2 minus 2 cosine theta d theta. And we can factor out the 2. So we have square root 2, 0, 2 pi, square root 1 minus cosine theta d theta. Now, to integrate this, I'm going to use cosine squared. No. I'm going to use sine squared 2 theta equals, sine squared theta equals 1/2 1 minus cosine 2 theta. So we could call this theta and theta over 2. And then we could take the square root. We could multiply by 2, take the square root, so that square root 2 sine theta over 2 equals the square root 1 minus cosine theta. So then this equals 2, the integral 0 to 2 pi sine of theta over 2 d theta. So sine integral changes sign. So this is negative 4 cosine theta over 2, 0 to 2 pi. So this is negative 4 cosine pi minus negative 4 cosine 0. So this just turns to 8. So that's like circumference. Okay, so that's all the polar we have. Velocity and acceleration. So we have constant acceleration. Oh, that's not constant acceleration. So the acceleration is increasing in z. But we're given acceleration vector, and we're asked to find velocity and position. And then we're given some initial conditions. Initial conditions because it's at time t is 0. So yeah, for this problem, we'll just do a of t, and it's a vector, is 1, 2, 6 t, and then so v of t is the integral of a of t dt. So this is just t plus c1, 2t plus c2, and 3t squared plus c3. That's like the third component. And then we can calculate, we can find c1, c2, and c3 with the velocity j negative k. So v0 is j negative k. This is just 0, 1, negative 1. So we use this, we say this implies that we have 0, 1, negative 1 equals c1, c2, c3. So our velocity vector is t, 2t plus 1, 3t squared minus 1. So position would be the integral of velocity is t squared, integral t 2t plus 1, 3t squared minus 1 dt. t squared over 2 plus c4, t squared plus t plus c5, or c5, and then t cubed minus t plus c6. And then we use our initial position, 1, -2, 3. And then you can do that. So that's that problem. Find the position vector, the velocity, acceleration, and speed of r of t equals 3 cosine, 3 sine, t squared. So r prime of t is 3 sine, 3 cosine, 2t. Magnitude r prime is square root 9 plus 4t squared. So this 9, this comes from the square, the sum of these squares. Because this is like 9 cosine squared, and then this is like 9 sine squared. And you can factor out the 9, and then we know sine squared plus cosine squared is 1. And then we add this guy, which is just the square of this dude. 2t squared is 4t squared. So this is the speed. This is velocity. What else do we have to find? Acceleration. So r double prime of t. So this is v, and then this is a. This is acceleration. -3 cosine, -3 sine 2. So this is acceleration. Okay. So sine of 5t, cosine 5t, -12t. We want t at pi over 4. So t is r prime over magnitude of r prime. This is cosine 5t negative sine 5t -12. And you could take the magnitude of r prime of t and then plug in pi over 4, or you could just do magnitude r prime of pi over 4 and divide by that, and then of course plug in pi over 4 here and here. So this guy, let's just say this is r prime. Let's just keep track of them. This is r prime. So then r prime pi over 4 is, draw on the unit circle, pi over 4, square root 2 over 2. Oh, it's 5 pi over 4. Sped up a little bit. Okay, so 5 pi over 4 is down here, so they're both negative. Negative root 2 over 2. And then this one's double negative, so this is positive root 2 over 2, and this is negative 12. And then we can take the magnitude of this. So this would be square root, this would be square root 1/2 plus 1/2 plus 144, square root 145. So then t is equal to r prime pi over 4 divided by magnitude r prime pi over 4, which is just 1 divided by square root 145, negative root 2 over 2, root 2 over 2, negative 12. Oh, I totally messed up. You know what I did? I forgot the chain rule here and here. So we have a 5, we have a 5. This is actually 25, 25. So this is 169. So this is 13. So that changes this one. Yeah. So yeah, I just forgot the chain rule when I was differentiating. We know that d dt sine of 5t is 5 cosine 5t. This guy from the chain rule. Yeah, and so I guess the next step is to find n when we have this r. So n was t prime over magnitude t prime. So t is r prime over magnitude r prime, 5 cosine 5t, negative 5 sine 5t, negative 12, divided by 13. And then so t prime would be negative 5 over 13 sine 5t, negative 5 over 13 cosine 5t, 0. Magnitude t prime is 5 over 13. So n is negative sine 5t, negative cosine 5t. Yeah, 0. Let's see. Oh, we want it at pi over 2 or pi over 4. So yeah, at pi over 4, well, notice they're both negative. So if we plug in pi over 4, this would be sine of 5 pi over 4 and cosine of 5 pi over 4. Those are both negative because it's in the third quadrant. It's down here. So that will turn both of these positive. So n of pi over 4 is square root of 2 over 2, square root of 2 over 2, 0. Find AT and AN, the tangential acceleration and the normal acceleration. Um, okay, what formula did they use? Yeah, that looks like a pain. Okay, let's do acceleration dot in. And it's at pi over 4, so we can just do like r double prime of pi over 4 dot n of pi over 4. So r was sine, cosine, negative 12t. Okay, so we're going to do r double prime. And then we're going to plug in pi over 4. And we're going to dot this. (25/2) plus 25/2 is 25. So that was 8n. They got a different number. Yeah. Yeah, I don't know. I mean, I guess that's an exercise for you. This problem, a sub t and a sub n, because there's still a lot more to go over. I don't want to spend more time on it. But you have the formulas from this, and it should be, since you already calculated t and n, like I'm not even sure if this work is correct because it seems like a lot, and we got like a simple answer. But like you just take a dot t, right? A dot n if you want the tangential or normal components. Consider the curve on the interval. Find the unit tangent vector t in parametric equation of the line to the curve at the point 1, 0. Okay. E cosine E sine. Oh, I was doing that thing again. Hold on, guys. I have to restart my OneNote. Dang. Oh, okay. Here we go. Better. Sweet. So, yeah, we have this guy, and we want to find t. So r prime of t is e to the t cosine t minus sine t. This one is e to the t sine t plus cosine t. Magnitude of r prime is e to the 2t times cosine t minus sine t squared plus sine t plus cosine t squared. So this is e square root cosine squared t plus sine squared t times 2. This is square root 2e to the t. Yeah, that's right. And then, yeah, then you just divide them. So this would be e to the negative t root 2 times, well, r prime. So that just makes it cosine t minus sine t plus cosine t. And then we want to find the parametric equation of the line to the curve. I think it means tangent line to the curve. But yeah, so we're going to do at P10 implies T is zero. So the line is 1, 0 plus t times t of 0. I'll use s. I'll use s instead. So this would be 1, 0 plus s times 1 over root 2, 1 over root 2. So now onto arc length and curvature. we want to determine the curvature of a space curve. So find okay. So this is a curve in a plane. You can tell because this is 0. So this looks like wait, no, x is increasing. Looks like this. It's a parabola. Wait, no, they're flipped. Input z. So it's like the square root function, I guess, but like a parabola. So it's like this. Okay. So yeah, we want to determine the curvature, but we can use that two-dimensional curvature is equal to y double prime. Is that absolute value? Yeah, it's absolute value. 1 plus y prime squared to the 3/2. What was that? Oh, thanks. So yeah, we have y double prime magnitude y double prime 1 plus. So this is a function z to f of z. Z is real. And so like this is equal to, like this is like the y in the formula. So like this is like z double prime magnitude 1 plus z prime squared 3/2. So we can just do let me think about this. Yeah. So f prime is 2z. F double prime is 2. So then our formula will give us 2 divided by 1 plus 4z squared 3/2. The z is really t, so I'll just put t. And this should give us the same thing as their work. Yeah, ha! Look at this. They did a cross product. Yeah, I didn't write the solutions to this exam review, but the person who wrote this solution, they didn't realize that R was a plane curve. So they actually did the cross product, and then they took the magnitude, and then they took the magnitude of like 2 vectors. We didn't have to do that. We can just use our plane curve curvature formula. So that's nice. So that's the curvature for that dude. Determine the location of the curve after having traveled a distance of pi square root of 10 over 3. Equals L and R of t. So we traveled along a curve, and then it's this curve, 2t, 3 sine 2t, 3 cosine 2t. So this is L, this is the length, and we want to know what time it took us to travel this. So we have to use L equals A to B magnitude R prime. And we'll just set A to be 0, and we're looking for B. So R prime is 2, 6 cosine 2t, negative 6 sine 2t. Magnitude R prime is the square root of 4 plus 36, square root of 40, 2 square root of 10. And then we're going from 0 to b, 2 square root 10 dt equals, that's why the square root of 10 is there. So then solving this for b equals pi over 6. Because we take this, we integrate time, so this is a t, and we're evaluating from 0 to b. You could have picked any number down here, but this is the most simple. Could you have picked any number? Yeah, the difference will still be the same. Okay. And then you plug in your upper bound, then you plug in your lower bound. So this is 2 square root of 10 times b equals pi square root of 10 over 3, which tells you that b is pi over 6, like I said. So that's that one. Now we can get into partial derivatives. F of x, y is sine of 4x minus 3y. F sub x is 4 cosine 4x minus 3y. F sub y is negative 3 cosine 4x minus 3y. And then we evaluate at the given point, whatever it is, and then that would be our answer. This is another calculate the derivative, so I'll skip that. Use total differentials to approximate 6.1 squared plus 7.8 squared. 6.1 squared plus 7.8 squared. So we want to approximate this. We want to find what this number is. Use total differential. So, well, we know 6 squared plus 8 squared is 36 plus 64. Square root of 100 is 10. So we know something near it. So if we can find a function that like sort of like models this, then we can use total differential on it. So we'll just call the first component x, second component y. And then, well, we know that like delta z is approximately dz is equal to fx 6,8 times delta x. Delta x is just equal to 0.1 because that's the difference between 6.1 and 6. Plus fy 6,8 delta y. Delta y would just be negative 0.2. Okay, and then to actually approximate this value, we would have to add 10 to this. So this is so this would be delta z, and then delta z equals z1 minus z0. So this means z1 is delta z plus 10, and then z1 is what we're looking for. So yeah, you just calculate these partial derivatives, like fx would be 2x over square root x squared plus y squared, and the same thing for fy. And then you just do function evaluation. You just plug in 6 and 8, and then multiply by delta x. Then you do that same for y, multiply by delta y, and that's the answer. Let's do a chain rule problem. Let's see if I can do this. So you guys can see the problems. So z is a function of x, y, z. No, just x and y. And then x is a function of t, y is a function of t. We want dz dt at t equals 1. So dz dt is, we go this branch, partial z respect to x, dx dt. Then we go this branch. Partial, oh no, it's doing that thing again. Excuse me 1 second, guys. Close out OneNote. Okay. Plus partial z, partial y, dy dt. So dx dt is just 2t. Dy dt is just 1. Partial z, partial x. X of 1, y of 1, we can calculate that. That's just 2, negative 1. So like that's the point we're at. And then we can do like plug in t is 1. So this is like dx dt equals 2 times 1 is 2. And then plug in 1, we still get 1. So that's good. And then as for partial z, partial x, we'll evaluate this at 2, negative 1. So this is equal to 2y plus 2x, and we evaluate this at 2, negative 1. So this would be 4 minus 2 is 2. Partial z partial y is equal to 2x plus 2y. Evaluated at 2, -1 is 2. And so plugging everything in, we get dz dt. Partial z partial x is 2. Partial x partial t was 2. Partial z partial y was 2. Partial y partial t was 1. So this is 6. Okay. Let's do an extremum problem. Doing this one. So we need to find critical points. So fx equals 0, fy equals 0. Fx is 6xy plus 0 minus 6x. Fy is 3y squared plus 3x squared plus 3y squared minus 6y. Set these equal to 0. What do we get? So we can say x squared plus y squared minus 2y is 0. We could add and subtract 1. X squared plus y squared minus 2y plus 1 equals 1. X squared plus y minus 1 squared is 1. So that's about right here. And then this guy, we have 6x, y minus 1 is 0. So either x is 0 or y is 1. So we have only 2 spots where both of them are 0 at the same time. Here, 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 here. So this is the point 0, 2. This is the origin. This is 1, 1. This is -1, 1. And then these are possible extremum to determine if / what type you need discriminant. You need d equals fxx fyy minus fxy squared to classify critical points. Okay.